Nobody on the road, nobody on the beach. I feel it in the air, summer's out of reach. Empty lake, empty streets, the sun goes down alone. I'm driving by your house, though I know you're not home, and I can see you, your brown skin shining in the sun. You got your hair combed back and your sunglasses on, baby, and I can tell you my love for you will still be strong after the boys of summer have gone. Hello everybody, welcome to this week's edition of Video Notes for Mr. Flugum's AP Chemistry class. That's right folks, this is for AP Chem, so if you're here from my general chemistry class, it's the other video that I posted this week. And we'll be talking about a few things for chemical bonding, right? Rule of octet, ionic and covalent, and metallic bonds. A lot of this will be review, so that's why we're doing it in video notes. But I want to make sure you're solid on this information. Okay, so let's start with this, the rule of octet. Now this is not a hard, fast rule, okay? It's just kind of a guideline that helps us understand why atoms tend to do the things that they do, right? So the basic rule is this, right? Elements tend to gain, lose, or share electrons in order to gain a full octet. What we mean by octet is 8 valence electrons, right? So when we say valence electrons, that means outer level, right? So 8 outer level electrons. So that means this, for the first level, actually a full octet is only 2, because there's only an s orbital, right? But once we get above level 1, that means a full octet is 8 electrons, full s and p sublevels. Now if you notice here, that just matters for s and p. We're not too worried about the d or f sublevels. Alright, so we can predict whether atoms will gain, lose, or share electrons. Alright, and that has to do based on its location on the periodic table. Okay, basically elements over here, right, and I'll draw kind of a line right there. Elements over here, these are metals, right, on the left hand side of the periodic table. They tend to lose electrons, right? They lose electrons and become positively charged ions, right? So metals lose electrons, right? Over here, okay, we have our nonmetals and metalloids, right? And what they tend to do is they tend to gain electrons, right? So they'll gain electrons. Remember, these are more electronegative over here, right? More electronegative, less electronegative. And that's part of the reason why. Now, these down here, right, if you're wondering about the actinide and lanthanide series, they are metals as well, right? So they tend to go into that category. Okay, now let's compare and contrast ionic bonds versus covalent bonds. Okay, so the first difference is this, right? With ionic bonds, electrons are gained and lost. So one atom will gain, and therefore another atom has lost electrons, right? The covalent bonds, electrons are shared. That's our first big difference. And so our next difference is this, right? When we have ionic bonds, we have positive and negative charges, right, that are holding the atoms together. In covalent bonds, those shared electrons are holding the atoms together. Since both atoms, need those electrons, they have to keep in close proximity to one another. Our next difference is this. Remember this, right? How do you tell them apart? Well, ionic bonds are always between a metal and a nonmetal. The only exception to that is ammonia, right? So there's our exception is our NH4 plus ion, right? Whereas if we have a covalent compound, it's 2 or more non-metals, right? So that's really key in us being able to tell the 2 of them apart, right? What's an ionic bond and what's a covalent bond. Alright folks, so last thing I want to talk to you about is with these, one difference is in the way that they're structured. So ionic bonds have what's called a crystal structure, where many of the formula units come together in order to form the ionic compound. For example, NaCl is never just one Na and one Cl. It's many of those atoms put together in a structure. However, molecules, covalent compounds, which are called molecules, like CO2, are standalone units. You can have one CO2 molecule. There's some differences there in the way that they form, right? Because of the differences in their bonds. Now we'll get into what NaCl is like in its structure and why it does that. All right, last thing I want to talk about is metallic bonds. These are bonds that occur between metal atoms. And this is generally between atoms of the same metal, but it can also work when you have two or more metals that are being mixed together. For example, when you're making brass, which is made of copper and zinc. What happens is this, right? We have a bunch of electrons that are kind of free floating or not attached to any specific atom. Usually these are the valence electrons in the metal, right? And because they are delocalized, they don't need to stay with the atom, right? They can move freely. That's what makes metals such good conductors, right? And then you can see here we have a lattice of positive ions, right? So these ions come and form the structure and the bulk of the metal, okay? So for example, this may be a piece of sodium, right? Because you have positively charged atoms that have a +1 charge, and you have approximately 1 electron per atom that can move freely. Okay? Now this explains a lot of characteristics about metals, like I said, with their conductivity, but also because there is no definite bond between any one atom and electron. This also gives you a reason to see why metals can be malleable, which means they can be pounded and molded, right? Or ductile, which means they can be drawn out into long rods or pipes, right? So this characteristic of metal bonds explains the characteristic of metals. Well, thanks for tuning in, you guys. I hope you have a great day, and I will see you in class. Bye-bye.